In today's class, we're going to be investigating piecewise functions. Now, you might be wondering, why are we learning about piecewise functions? A lot of real-life situations are better modeled by piecewise functions as opposed to a single function. So by the end of today's class, you should be able to do the following two things. Develop a real-life example where a piecewise function is necessary to model the situation, and create your own piecewise function, whether it's creating the equations for it or creating the graph for it. So let's take a look at one of the most famous piecewise functions that we know, the absolute value function. So if you take a look here, we have the absolute value function, which is y equals to the absolute value of x. Now, in our case, absolute value brackets, the two kind of straight lines that you see next to x there, they turn any integer that you put inside there positive. So if you take a look here, you're wondering, how did we get this graph? So if you're unfamiliar with the absolute value function, let's do a table of values to help us visualize what's going on first. So I'm going to make my table of values on the side here. And I'm going to do a variety of x values. So I'm going to do, let's say, -4, -3, -2, -1, 0, and then 1, 2, 3, and then 4. And I've got y equals to the absolute value of x. So in this case, let's say my x value was -4. If I plug it into my absolute value, that's going to spit me out something positive. Same thing with -3, that's going to spit me out something positive. Same thing with -2. Same thing with -1. And then the absolute value of 0, that's just going to give me 0. And then if I do the absolute value of a positive number, it's just going to give the same number. So it's going to give me 1, 2, 3, and then 4. So if we take a look at my table of values and the graph that's created, which is on the left-hand side here, this is the graph of the absolute value function. It kind of looks like a V shape. And, a lot of the times students will kind of associate absolute value functions looking like this. Now, if you take a look at this, it's actually composed of two different functions. And the domain is split up into two parts. You have everything that's less than 0, and then you have everything that's greater than or equal to 0. So if I take a look here at the bottom, I've broken up the absolute value function into what we call a piecewise function, into pieces, so we know how to graph it. So if I take a look here at the bottom, f of x, which represents my absolute value function up there, it has two parts. My function is x if x is greater than or equal to 0, and then -x if my x values are less than 0. So let's match up the pieces from my piecewise function with the graph that I've got there. So if I start off, I've got y equals to x if my x values are greater than or equal to 0. That is dealing with this portion here. As long as your x values are bigger than 0, then your graph can be modeled by the equation f of x equals to x. But if your x values are less than 0, which is on the left-hand side of the graph here, then the equation that models that particular portion is going to be -x instead. So the absolute value function is composed of two separate functions. You have x if x is greater than or equal to 0, and then -x if your x values are less than 0. Now, like I said, this is the most famous piecewise function that we know about. Let's take a look at another graph now, where it isn't a absolute value function, and let's see if we can come up with the equation for the piecewise function instead. So in part 2, it says develop your own piecewise function. And in this example, it says develop your own piecewise function using the graph. Now, when you take a look at your graph here, notice that your graph is in pieces, right? It's not a full parabola, it's not a full line, so we've broken this up a little bit. And the first thing you have to notice is what value of x is your piecewise function breaking up at. So in this particular case, I know that there's no scale here, so I'm going to write in a quick scale for you guys. so that you see it. So technically this should be 2, and then this is 4, and then this is 6. This is -2, this is -4. And then this here is also 2, and then 4, and then 6, and then 8. So when I take a look at this piecewise function graph, I notice that everything important is happening at x equals to 2. So what I'm going to do is I'm going to make a dotted line just so that I know that at x equals to 2, something is going on. Okay, which means that's where our pieces are going to be created. So if I'm creating my piecewise function, I'm going to start off by saying that this is f of x. I'm going to call this whole thing here f of x. So I'm going to have f of x equals, and here is the fun part. If we take a look at my piecewise function, at x equals to 2, I've got 3 different things happening. I've got the potential of a parabola, I've got a dot, and then I've got a line. Okay, so let's talk about everything that's less than 2. So I'm going to start talking about this portion here first. So I'm going to talk about everything that's less than 2. So in my domain that I'm breaking it up as, I'm going to talk about if x is, now be careful here. If I'm taking a look at everything less than 2 here, that deals with the parabola. Look very carefully at the bubble at x equals to 2 for my parabola. That's an open bubble, which means x equals to 2 is not included in this particular portion. So I'm going to say x is less than 2. So if I'm taking a look at that portion there, I notice that on the left-hand side of 2, I've got this parabola. So that means when x is less than 2, the portion of the graph can be described by x squared. And then I notice I also have everything to the right of x equals to 2. So if I'm dealing with everything to the right of x equals to 2, that means I'm dealing with if x is greater than 2. And again, because I'm dealing with everything to the right of 2, notice that I'm dealing with the line. Now the line has an open bubble at x equals to 2, which means x equals to 2 is not included in this domain. So the graph that represents this, it actually ends at 6 and it's a closed bubble. So I'm going to fix that domain there. It's going to be between 2 and then including 6. So this portion here, represented by the green line that I'm highlighting, that represents that portion of the piecewise function, which is 10 minus x. Now you might be wondering, why do I have a gap there? There's actually a third component. In my domain here, for the red portion, I had x is less than 2. And then in the green portion, I had x was greater than 2. But none of them included x equals to 2. So in this particular case, at x equals to 2 for us, we're looking at that closed bubble now. We're looking at this bubble right here. That has a value of 6. And that is when x is equal to 2. And so what we've done here is we've created the equation for the piecewise function that's represented in this graph. Think of it this way, like I said, take a look at your piecewise function, notice where all the commotion is happening. Draw a dotted line and then take a look at the left-hand side of that dotted line, the right-hand side of that dotted line, and then right on the dotted line. That's going to help you create your piecewise functions a little bit easier. Let's take a look at this example. It says a car rental company charges its customers a set fee of $50 for a weekend. On top of that, they charge 25 cents per kilometer for the first 100 kilometers traveled, and then 15 cents per kilometer for any distance exceeding 100 kilometers. So in this particular problem, we're using piecewise functions here to help us because we're going to actually have 2 different lines that are going to create the total cost of renting this car. So part A asks us to draw a graph to model the cost versus the distance traveled. So I'm just going to make my axes first. So I've got my cost axis, and then I'm going to end up having my distance traveled axis. So this is going to be my distance, D for distance. I'm just going to write here, let D represent distance, and then let C represent cost. So I've got D here, and then I've got C here. And I know that something happens at 100 kilometers. So I know that at 100, that's an important number for me on my x-axis. Now, we then have to think about what's important on my cost axis, right? Because there's going to be certain times where my graph is going to change. I know that $50 is my set fee. So I'm going to put that in. I don't have a scale here, like I don't have graph paper, so I'm doing a rough sketch. So I'm going to put $50 in here. So we know that that's the set fee for the weekend. Now, here's what I know. At 100 kilometers, I'm going to be changing the cost per kilometer. So something else is going to happen at 100 kilometers. So I need to know at 100 kilometers, how much will it have costed me to rent my car? So if I'm taking a look at 100 kilometers, the first 100 kilometers is 25 cents. So that means it's going to be $25 for the first 100 kilometers plus the $50, which is going to give me a total of $75. So I know that something is going to happen at 100 kilometers driven and when my total cost is $75. So let's take a look at plotting the first part of this piecewise function. The first part deals with this portion here that I'm highlighting. It's $50 for the weekend and then 25 cents per kilometer for the first 100 kilometers traveled. So if I'm traveling anywhere from 0 to 100 kilometers, I'm going to be charged 25 cents per kilometer. So I'm going to start at 50, and I know that at 100 kilometers, I'm going to have to pay $75 in total for that weekend. So I'm going to draw my line to connect that. And then I know that after 100 kilometers, though, I'm only being charged 15 cents per kilometer. So if you go back to grade 9 and you think about this, these are dealing with slopes. The rate of change here per kilometer is dealing with the slope. So if my first line was 25 cents per kilometer versus 15 cents per kilometer, that means the second portion of my graph should have a more flatter slope compared to the first portion. So if I draw in my second portion, it should have a flatter slope. And because that deals with 15 cents per kilometer, while this one here deals with 25 cents per kilometer. And there we go. We've created a rough graph that represents cost versus distance. And we notice here that this is a piecewise function. Let's take a look at B now. So for B, it says determine the function that models this particular situation. In other words, we want to create the equations that represent this piecewise function. Now, I already have my let statements up at the top. I said let D represent the distance and let C represent the cost. So let's start off with the most obvious piece first, which is the first portion of our piecewise function. So if I'm doing C for cost, it's going to be split off into two different functions here. The first portion, which I'm going to highlight yellow on the graph above, this one should be relatively straightforward for us to figure out. That one there, we know the slope is 25 cents, and we know that the starting cost is $50. So I'm going to have 0.25 times D plus D. I'm just going to extend my highlighting. And we know that this is valid for if you're traveling between 0 kilometers all the way up to 100, and including 100 kilometers. Now, we have to think about the second portion, which is the portion that I'm going to highlight in blue. Now, you might be going, miss, I know that the slope is 0.15 because it's 15 cents per kilometer, but I don't know what the starting cost is because that's a different line there. And then now we got to think about, how do I figure that out? Well, let's take a look at that work on the side then. So on the side, I'm just going to say for second portion. Now, let's talk about the total cost if you were to travel more than 100 kilometers now. So if you were to travel more than 100 kilometers, we know that it would be 0.15, right? Because it's 15 cents per kilometer. And technically, it's whatever distance you traveled minus 100, right? Because the first 100 kilometers is at a different rate. That's why we're doing D minus 100 here. Because if you traveled, let's say 150 kilometers, then we've already dealt with the first 100 kilometers being a certain price. And then you're dealing with the 50 kilometers later that will be at 15 cents per kilometer. Plus 75. So here's how I'm doing everything. This represents the cost for the first 100 kilometers. And then this whole thing here deals with the cost for after the 100 kilometers. And so combined, that's going to give us the total cost of renting that car for the weekend. So we're going to simplify that to make it look a little bit nicer. And when you do, you're actually going to end up getting the following: 0.15D plus 60. So that represents the second portion of your piecewise function. So I'm going to have 0.15D plus 60 if you're dealing with a distance that is going to be greater than 100. And there we go. That's the piecewise function that represents the situation in the graph that we have there. Let's take a look at part C. For part C, it says, how much will it cost to travel 500 kilometers over the weekend? Now you have to be careful for this one here. Because of your piecewise function, you need to take a look at which piecewise part are you going to be using to help you solve this question. So we're looking at 500 kilometers. 500 kilometers is more than 100, which means we're going to use the blue equation to help us out. So in this case, I'm going to do C equals to 0.15 times 500 plus 60. And if I simplify that, I'm going to get 135. So that means, therefore, it will cost $135. Now, let's say I was looking to see how much it costed for 45 kilometers. Since 45 kilometers is less than 100, then I would use the yellow highlighted equation instead to help me figure out my total cost. So it depends on in our case here, the D value. Does it belong in the section where it's between 0 to 100, or is it bigger than 100? So we've done some examples in terms of piecewise functions. It is something that is very new, and I do recommend to practice. So practice graphing as well as practice creating the equations of piecewise functions.